Hello dear viewers, this is AI Voice Gary, speaking to you as Buddy from Town's narrator. Since Buddy began his exploration of the cosmos, he has become interested in current news about the universe. Today, Buddy from Town is sharing news about scientists resolving the black hole fuzzball or wormhole debate. The January 4, 2021 article by Laura Arinshield of The Ohio State University discusses a new study, published on December 28 in the Turkish Journal of Physics, that says, black holes really are giant fuzzballs. Arinshield's article posted on Phys.org explains that the study attempts to put to rest the debate over Stephen Hawking's famous information paradox, that is, the problem created by Hawking's conclusion that any data that enters a black hole can never leave. This conclusion accorded with the laws of thermodynamics, but opposed the fundamental laws of quantum mechanics. Fuzzballs are theorized by some superstring theory scientists to be the true quantum description of black holes. The theory attempts to resolve two intractable problems that classic black holes pose for modern physics. First, the information paradox, wherein the quantum information bound in and falling matter and energy entirely disappears into a singularity. That is, the black hole would undergo zero physical change in its composition, regardless of the nature of what fell into it. Second, the singularity, at the heart of the black hole, where conventional black hole theory says there is infinite spacetime curvature, due to an infinitely intense gravitational field from a region of zero volume. Modern physics breaks down when such parameters are infinite, and zero. Arinshield notes, the study found that string theory almost certainly holds the answer to Hawking's paradox, as the paper's authors had originally believed. The physicists proved theorems to show that the fuzzball theory remains the most likely solution for Hawking's information paradox. The researchers have also published an essay showing how this work may resolve long-standing puzzles in cosmology. The essay appeared in December, in the International Journal of Modern Physics D. Samir Mathur, lead author of the study, and professor of physics at The Ohio State University, said, "What we found from string theory is that all the mass of a black hole is not getting sucked into the center. The black hole tries to squeeze things to a point, but then, the particles get stretched into these strings, and the strings start to stretch and expand, and it becomes this fuzzball that expands to fill up the entirety of the black hole." Mathur published a study in 2004 that theorized black holes were similar to very large, very messy balls of yarn, fuzzballs, that become larger and messier as new objects get sucked in. The bigger the black hole, the more energy that goes in, and the bigger the fuzzball becomes, Mathur said. The 2004 study found that string theory, that is, the physics theory that holds that all particles in the universe are made of tiny vibrating strings, could be the solution to Hawking's paradox. With this fuzzball structure, the hole radiates like any normal body, and there is no puzzle. However, the article notes that a section of people in the string theory community itself thought they would look for a different solution to Hawking's information paradox. Mathur said, they were bothered that, in physical terms, the whole structure of the black hole had changed. Arinshield's article notes that studies in recent years attempted to reconcile Hawking's conclusions with the old picture of the hole, where one can think of the black hole as being empty space, with all its mass in the center. One theory, the wormhole paradigm, suggested that black holes might be one end of a bridge in the space-time continuum, meaning anything that entered a black hole might appear on the other end of the bridge, the other end of the wormhole, in a different place in space and time. In order for the wormhole picture to work, though, some low-energy radiation would have to escape from the black hole at its edges. This recent study proved a theorem, the effective small corrections theorem, to show that if that were to happen, black holes would not appear to radiate in the way that they do. Small corrections resolution to the paradox suggests, Hawking's computation fails to keep track of small corrections that are eventually sufficient to preserve information about the initial state. This can be thought of as being analogous to what happens during the mundane process of burning. The radiation produced appears to be thermal, but its fine-grained features encode the precise details of the object that was burnt. This idea is consistent with reversibility, as required by quantum mechanics. It is the dominant idea in what might broadly be termed the string theory approach to quantum gravity. Laura Arenshield's article notes that the researchers also examined physical properties from black holes, including topology change in quantum gravity, to determine whether the wormhole paradigm would work. In each of the versions that have been proposed for the wormhole approach, we found that the physics was not consistent, Mather said. The wormhole paradigm tries to argue that, in some way, you could still think of the black hole as being effectively empty with all the mass in the center, and the theorems we prove show that such a picture of the hole is not a possibility. This concludes Buddy's Space News today. If you would like to follow along to see Buddy from Town become Buddy of Singularity, please click subscribe, and a like would be appreciated. Until next time, dear viewers, keep looking up and looking back, way back.